and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the Fkg inequality. So what is this? Well, let's remember from last time the Four Functions Theorem. So the Four Functions Theorem of Allsweet and Dakin from 1978 said that if we had four functions, alpha, beta, gamma, delta, from families of sets to the non-negative reals, and if for every a and b set, the inequality alpha a, beta b was the most gamma of their union and delta of their intersection, then actually more generally for families of sets a and b, script a and script b there, then the same inequality holds where those are meant to be the sums then. So alpha of script a is the sum of alpha a over the elements in script a, and so on for the rest. So this was our famed Four Functions Theorem, which we proved last time. We also extended it to lattices, where we let L be a finite distributive lattice, and then if we had four functions, and if for every two elements x and y of the lattice, the inequality seen there holds, then for every sets x and y, the inequality holds. So these were the four function theorems, the normal and for the lattice. Now, today we'll use them to prove the Fkg inequality and Kleitman's lemma. So let's get to the Fkg inequality. This will be about lattices. So we let L be a finite distributive lattice. A function mu from the lattice to the non-negative reals is called log supermodular. If for every x and y in L, we have that mu of x, mu of y is at most mu of the meet and the join there, the product of those. So this would be log because we're doing products instead of sum, and supermodular has the inequality that way. If it was modular, it would be equal, and submodular, the inequality would go the other direction. So we'll say that's log supermodular. We need two more definitions. We say a function on the lattice is increasing if f of x is at most f of y whenever x is smaller than y in the lattice, and decreasing if the reverse holds. So quite natural. So given these definitions, we can now state the Fkg inequality of Fortuyn, Castellan, and Ginebra from 1971, which says let L be a finite distributive lattice, and mu a function that's from the lattice to non-negative reals that's log supermodular. Then, if f and g are functions that are both increasing, then we have the following inequality. This is the Fkg inequality. So what is this? It says if I take the sum over the elements x in the lattice of f of x times mu of x, and take that whole sum and then product it by another sum where I'm doing that with g of x, mu of x, then this is the product where I take f and g together in the sum first, and then in the last term there I leave f and g out. So what is this saying? So if I have this product, really we can move g from one term to the f term, and that only increases the function, the inequality, this product. So that's when they're both increasing. What happens, you might wonder, so I also define decreasing. What if they're both decreasing? Well, actually the same inequality holds. So you have this nice transference property also when they're both decreasing. Well, you might wonder what happens if one is one and one's the other. So if f is increasing and g is decreasing, or vice versa, then actually the inequality becomes reversed. And so I won't write that out, but you get this reverse inequality. So if they kind of both go in the same direction, we can make this move. If they go in different directions, then actually doing that switch would create a decrease. Okay, so why is this? Well, we'll note that it suffices to prove only the case that both are increasing, and the question there is why. So I only stated it for increasing. You'll be able to see, and we'll go through that the proof could obviously be tweaked for increasing and decreasing, or both decreasing, etc. But actually, the statement from just increasing alone is enough to derive the others. So why is that? I might pause the video and think for a moment. There's a small trick to see why that's true. Here's that trick. Well, if one of them was decreasing, or both, so if we have phi and fg, what we instead use is we define phi prime, where I take the max over all the elements of the lattice of phi of x minus phi. So I think of the negative from the max, so the distance from the max there. That will become an increasing function, as the max would just be a constant, and then we'd have a negative, so it flipped the sign, we get an increasing function, and because we shift by that max, we ensure it's non-negative. So then we could just apply the Fkg inequality with this altered function. And you would find that, of course, that means, so if they're both decreasing, there's some other terms there that end up canceling out, but you have the signs kind of a double negative, and you end up with the same inequality. If only one is, then after you cancel like terms, you end up with the inequality reversed, as you'll have an extra negative on both sides. So that tells us it's enough to prove the Fkg inequality for increasing functions. So let's go on with the proof. How will we prove this? Well, we're going to use the Four Functions Theorem. So we're going to define four functions, alpha, beta, gamma, delta, to apply the Four Functions Theorem with. Here will be those functions. For alpha and beta, and again for every x and l, we naturally take alpha to be f times mu, and beta to be g times mu. And then what do we take to be gamma and delta? Well, gamma will have, because they're both increasing, we're going to use f times g times mu, and for delta, we'll just use mu. And that should make sense because those were somehow the individual terms coming up in the inequality. So now in order to apply the Four Functions Theorem, though, we have to show that the condition holds. So let's go through that. Let x and y be elements of the lattice. Then since mu is log supermodular, by definition, that is mu of x, mu of y is at most the mu of the meet and join. And then since f and g are increasing, their f of x is at most the join of x and y, and g similarly is at most the join there. And so then what is the four functions condition? Well, we have alpha of x times beta of y, so we could just plug that in. You'd have an f mu for x and a g mu for y. And then from the inequalities above, let me do a little rewriting. So let's move the mu to the end. So we have f of x times g of y times mu of x and mu of y. And then from the inequalities above, well, we could upper bound this with the f of the meet, the g of the meet, and then by log supermodularity, the mu of the meet and the join. And then, well, if you look at those first three terms, that's just gamma of the meet, of the join, and then we have delta of the meet there for our mu of x. So that's what we end up with, which is exactly the condition we need to apply the Four Functions Theorem. So that alpha of x, beta of y is at most gamma of the join, and delta of the meet there. But let's apply it now, so thus the conditions hold. So by the Four Functions Theorem, again for lattices, we have to apply it for certain subsets of the lattice. We're actually just going to apply it where x and y are the whole lattice. We know that alpha of L times beta of L is at most gamma of L delta of L. And that is precisely the inequality that we want. So we take the sum of x and L of alpha, x, which is f times mu, for beta, which is g times mu, gamma, which is f times g times mu, and for delta, which is just mu. And then we're done. So that finishes the proof. So it's a rather easy application of the Four Functions Theorem. And how would you do the other cases? So one, you could obviously just reduce them as we did before, but actually the same proof works if you choose kind of different functions. So for both decreasing, you would swap gamma and delta, and then you would see that the inequality, the condition still holds when you do that swap, because now instead of being, instead of using the increasing property to go up to the join, you use the decreasing property to go to the meets. If one was increasing and decreasing, so say f was increasing and g was decreasing, you could still do this. You'd modify it. We'd have alpha be f times g times mu and beta be mu, which are kind of the opposite ones, the gamma and delta from before. And then you have gamma be f times mu and delta be g times mu. And you could check again the condition works for those ones. So that's the Fkg inequality. Let me tell you about a slightly alternate formulation, which may be easier to remember and has more to do with probability. So it's helpful to view mu as a measure on the lattice. What do I mean by that? Well, if I had a finite distributive lattice and this function that's not identically zero, then we can think of that function as having somehow therefore weight on the lattice, and then we can define the expectation. We can view mu as a measure then, and then we can define the expectation of a function, f, with respect to mu as the following. You would define it to be the sum over x and L of f times mu divided by mu. So if you thought of somehow mu as being a measure, then if we normalize it all by taking the sum over all the elements of the lattice, then this would be indeed somehow the probability of f. So therefore the expectation of f, where you sum each point with that probability. So this is quite natural from a probabilistic standpoint. And then we can make an alternate formulation of the Fkg inequality. Namely, if L is a finite distributive lattice and mu is log supermodular, and if f and g are both increasing or decreasing, then really that huge inequality can best be reduced to the following simple one, that the expectation of f times g is at least the expectation of f times the expectation of g. So when viewed then in this expectation, which makes a lot of sense. Somehow we're saying that when we product them together, we expect that product, if they're both increasing or decreasing in the lattice, to actually be bigger than the individual products. And if one is increasing and the other is decreasing or vice versa, then that product we expect to be smaller. So somehow they're working against each other in that case. So this makes a lot of sense, and that's a compact way to remember the Fkg inequality. And you'd get that just by taking the original one and dividing through by factors of the sum of mu, that factor squared. All right, so we won't, of course, prove that. It's just an alternate formulation, but we said the other one first, just to give kind of a different view, and then here's a more compact view. And now we can turn from that towards Kleitman's lemma, which are really kind of an application of the Fkg inequality. So we say a family of sets, a subset of 2 to the n, so that's a family of sets, subsets of n, is monotonically increasing if for every a in A, all of the sets above A are in script A, and monotonically decreasing if the alternate holds. So it's downward closed, that all the sets, all of your subsets are actually in the family as well. So that's quite natural. And then we define the probability of A to be simply the size of A over 2 to the n. So if you think of a probability space where it's uniform over all the possible sets, then this would be the probability that you'd be in A, script A there. Okay, so that, given those terms, those definitions, we can state Kleitman's lemma, which we stated before, but let me go through it in a little bit more generality now. So if I had 2 families of sets, if both are monotonically increasing or both are monotonically decreasing, then the probability of their intersection is at least the product of the probabilities. So you can view this if you times by 2 to the n as some kind of counting argument, but it's maybe better to think of it in this probabilistic terms. And then, so that essentially they're positively correlated. Whereas if A is monotonically increasing and B is monotonically decreasing, or vice versa, so if they're differing in monotonicity there, then the inequality is reversed. They're less likely to have an intersection. So that's Kleitman's lemma. So let's go ahead and prove this. So we can just derive it. You could derive it from the Four Functions Theorem, but we can also derive it from the Fkg inequality. So first, suppose A and B are both monotonically increasing, so as we did for the Fkg inequality. And what would you do here? Well, you want to apply the Fkg, so you let f be the characteristic function of script A, which is f of A is equal to 1 if A is in script A and 0 if it's not in the family. So you just put a 1 when you're in the family and 0 when you're not. This creates a function. And similarly, we'll let g be the characteristic function of B, so it's 1 if you're in B. If you look at it then, if both are monotonically increasing, then it means that f and g are increasing, right? So we have these family of sets, subset inclusion made a lattice. So of course this is increasing, right? Because then they're upward closed. So they're very simple increasing functions, just 0, 1s, but very nice. And now we can apply the Fkg inequality. We need a log supermodular function, but here we just use mu being always just 1, which is, of course, every constant function is log supermodular. Then we'd have that the probability of A intersect B, if you write it out, it means precisely this, the expectation of f times g, which is at least the product of the expectations by the Fkg inequality, which are indeed the probabilities. So you can work that out, right? We'd be interested in where A intersect B, which happens to be 1 when both f and g are 1, when you're in both sets. So that is indeed that product there. So that's a very nice use of the Fkg inequality, and the other cases would follow similarly. So we'd use characteristic functions, and you'd have them be both decreasing if they're decreasing, and you get the same sign, or if they're opposite, then the sign is reversed. And you could also use a different tactic. You could derive both from monotonic increasing, because you could look at the complementary families, which would then be monotonically, if they're decreasing, the complementary ones be increasing, and you could derive with a little arithmetic. So that's the proof of Kleitman's lemma. So again, this is all in the space of these correlation inequalities. So when are two things somewhat correlated? And that's really, the Fkg inequality is a really nice way to view that. So if somehow an f and g are both increasing on a distributive lattice, then you can somehow think of their product is indeed correlated. And same for decreasing, and opposite, that they're negatively correlated if they have kind of opposite increasing decreasings. And we can do that too then with the family of sets, where we just take the uniform measure. We can do a probability p version, which is quite nice. So here we let p be a real vector, p1, pn, or for every I, pi is in 0, 1. Then you could consider a probability space on just the family of all sets, where a random set is chosen by choosing I and n independently with probability pi. So instead of thinking of all the sets as being equally likely, it's quite natural to think where, element 1 is in with some probability p1, and then 2 with some probability p2, and this creates a new probability distribution on the sets. Namely, the probability of A, which we'll write as mu pa there, would be the product of I and A of pi times the product of j not in A of 1 minus pj. So it creates a somewhat non-uniform distribution there. And the claim is that this is actually still log supermodular on this lattice. So how would you prove that? You might want to stop and prove it for yourself. Well, basically the answer is it's actually log modular. So for A and B, they're actually mu of A times mu of B is actually equal to product of mu on the union times mu on the intersection. Why? Well, each pi term, so you'd have the product of the pi's for I and A and for I and B. Well, that you could split up for A union B and A intersect B exactly, and the same with 1 minus pj. So they'd appear the same number of times on both sides of that inequality above. So you can do that out, but that's essentially the proof. So now that we know this is a nice other kind of function that's log supermodular, where you come from this independent choices with the pi. So from that, you can get a more general version of Kleitman's lemma. So namely, for every family of sets A, you define probability P of script A to be the sum over its elements, A in script A, of the mu P A, this measure there. Then the Fkg inequality, if we instead use this other type of measure, this mu P, gives that if A and B are both monotonically increasing or decreasing, then for any real vector, under this probability measure, probability of A intersect B is at least the product of the probabilities. So they're correlated even under this weighted measure. And then if one is increasing, the other decreasing, the inequality is reversed. So that's quite nice as well. And there could be other log supermodular functions. These are somehow the two nicest to use on all the set. And then from that, we could get applications. So let me just do one simple application, and then we'll talk about graphs, as this is for combinatorial purposes. So here's one simple application. Let A1 to AK be subsets of n, 1 up to n. So let A be a random subset of brackets n there, where each I is chosen independently with probability pi. So this is quite natural. It's like what we had before, but we have fixed sets. We have fixed k subsets. And then here's a nice proposition. We claim that the probability that A intersects each of these sets AI is at least the product of the probabilities. So let's go ahead and prove that. So proof, well, I'll just use our theorem there. So we have to define appropriately a family. So I define script AI to be the subsets where A intersect A is non-empty. You do this for every I and K. And then script AI is a monotonically increasing family, right? If I add in more elements, then it doesn't ruin, then I'm still intersecting. And then what does that give us? Well, you'd repeatedly apply the previous theorem to define that the probability in script P of, which is this weighted measure, which is what we get in the proposition, the probability of the intersection of all these families is at least the product of their probabilities, which is the proposition as claimed. So think about what that's saying. So we have this setup where we're doing this random choice with these strange probabilities, and I have these sets. We're saying it's likelier to intersect all of them than you would just get by independence. Well, that's a beautiful statement, but it's not really clear why that should be true. So what do I mean? Calculating the probability that A intersects AI is not so hard, right? You just 1 minus kind of the product. You have to make sure that you don't end up having, the product, the 1 minus the PIs for all the things in AI. So you could easily calculate the right-hand side. The left-hand side is much more complicated, right? You could have various overlaps of all the various A's. So if you try to use inclusion-exclusion, it could get very messy, and it won't be clear that this should hold. But yet, our Fkg inequality, our Kleitman's lemma things, allow us to just easily see, oh yeah, these are monotonically increasing properties, so they hold. And if they're all increasing or all decreasing, then we can actually apply it repeatedly and get indeed this multivariable version. If you only have two if you have one increasing, one decreasing, then you could only do it with two there. But if you're all one direction, it works all together, actually. So that's one application. Then our last application is on graph properties. So we say a graph property P is monotonically increasing if adding edges preserves P, and monotonically decreasing if deleting edges preserves P. So this is quite natural, and this is what actually started our motivation in the beginning. We talked about planarity and Hamiltonicity. So planarity is monotonically decreasing. If you delete edges, it stays planar. Whereas Hamiltonicity, for example, is monotonically increasing. Adding edges preserves Hamiltonicity. And then the previous theorem now implies the following, that if you let P and Q be graph properties, then if they're both monotonically increasing or monotonically decreasing, then the probability that G and P, this random graph from the Erdős-Rényi model, has P and Q, has both of those properties, is at least the product of the probabilities. Probability that G and P has P and the probability that G and P has Q. And vice versa, if one's increasing and one's decreasing, then the inequality is reversed. So this is what we started to motivate it all. We asked, okay, we have the Erdős-Rényi random graph model, G and P, and think about the events where you're planar or you're that you're actually Hamiltonian. And then we asked, well, how's the correlation with these? And this would indeed tell us the inequality is reversed, that they're negatively correlated. And that holds not only for these, and generally for any monotonic properties. So if I have two monotonically increasing properties, then indeed somehow it's more likely in G and P to have both than if you viewed them as independent. Same if they're decreasing, and if they're opposed, then actually they're negatively correlated. So that's our last example there. So today we went through the Fkg inequality, which somehow had to do with these measures. So the expectation of Fg is at least the product of the expectations if they're both increasing or decreasing, or reversed if they're opposite. And then we use that to derive Kleitman's lemma, which is really about families of sets there, and you can even do it with measures that aren't uniform. So we could do these probability P measures to get facts about graph properties with the Erdős-Rényi model. And thus we conclude our talk about the correlation inequalities. So we did the Four Functions Theorem, which was quite nice, and then today we saw all the applications of it, or many of applications of it, that the things you think to be obviously true, this increasing and decreasing, we can actually rigorously work out the math with some subtle arithmetic tricks. It's not really trivial at all, as you've seen, but to indeed prove that what we thought should be true is actually true. So until next time, see you then.